This is video 3 in this simulation and Simio refresher module. And in this video, what we're going to do is talk about the tandem queuing system that we're going to use throughout the remainder of this module, and then go ahead and build the baseline Simio model. So a tandem queuing system looks like this. And so we basically have two servers, and we can think of this as a manufacturing system or a service system. So in a manufacturing system, we would think about parts that arrive. In a service system, we might think about people that arrive. In the general simulation context, we call those all entities. And so in our tandem queuing system, entities arrive and they go through some service process at the first server. They then go to the second server and go through some additional service process, and then they're finished. So that's where the name tandem comes from. The queuing part comes from the fact that we have limited capacity. So in our model, we're going to have 1 unit of capacity here. And so you can see in the drawing that I have 3 entities that are waiting in line. So when an entity arrives, if there's capacity available, it immediately starts service. Otherwise, it waits in the queue. Similarly, when it finishes at S1, it moves to S2, and if S2 has capacity available, it immediately starts service. Otherwise, it waits in the queue. So just a standard queuing, tandem queuing model. Now, our model is characterized by the arrival and service processes, and so we're going to assume that entities arrive at the rate of 6 per hour, and that equates to a mean inter-arrival time of 10 minutes. And we're going to assume everything's exponential here for this initial model. And so the service rate at S1 is 7.5 per hour, which is a mean service time of 8, again, exponentially distributed. And for service at S2, service time of 9, which equates to a service rate of 6.67. So that's the basic tandem queuing model that we're going to use. And we're going to develop 4 different simulation models of this, illustrating or refreshing your memory on different aspects of Simio modeling. Model verification is an important component of modeling, and that's where we're demonstrating that the computer model, the Simio model in our case, behaves as we expect it does. And so we are going to use a queuing model to show that. We have a very simple queuing system. And so recall that if we have MMC queuing system, it's very straightforward to compute the steady state performance. And so if you're rusty on this, or if you haven't seen this in a while, this is something you want to go back and look in chapter 2 of the textbook, of the Simio and Simulation textbook, where we go through that. And I'm going to assume that we know how to do that. And so the model that we build, let me just drag this over here. Let me enlarge this here. Is a very straightforward model. Here's our queuing system again. And so we have on our arrival rate, and then we can compute we can put the individual station parameters in. So we have the service rate, the corresponding mean service time, and C is the capacity. So if you have an M1 queuing system, we have exponentially distributed arrivals, exponentially distributed service, and 1 unit of capacity. And once we have that, we can use the queuing formulas that I just showed to compute the utilization, the number of entities at the station, which is L, the number of the time that an entity spends at a station, which is W, and then we can compute those same metrics for the overall system. And so in our case, it's really straightforward because we have a linear system where all of the entities go to S1 and S2. And so our total number in system on average is 13, and our time in system is 2.7 time units, and our time units here are hours. So 2.7 hours that the average entity spends in the system. So now that we have our queuing model and we have some expectation of what the correct model should give us, let's build the base Simio model. And so the basic model building process in Simio is we're going to place object instances. In our case, we have 2 server objects, a source and a sink. We're going to connect those so that we can specify the entity flow. And then we're going to place the dynamic objects, entities. Then we're going to go back and set all the object properties, and then we're going to create an experiment to verify our model against our queuing model. So let's go into Simio here, and let's build this base model. So as I said, the first step that we're going to do is we're going to place our base object instances. So we're going to take a source, which creates the entities. Then we're going to take our 2 servers, so there's S1 and S2, and then we're going to place our sink. And let's go ahead and name these so that matches the naming of our model. or in our definition anyway. So there's S1 and S2. And so we place the main structure here, and we're going to use connectors to specify entity flow. So entities that arrive from the source or created from the source will then flow to the input at S1. When they finish at S1, they go to S2, and when they finish at S2, they depart. And so entities then depart the system. Then in the next step, we'll place our dynamic entity, our dynamic object. So now we're going to place an instance of model entity, which is our default entity. So also note, now that we have the basic structure of the model defined, we can actually run the model. So we haven't set any of the properties to specify the arrival process or the service process, but as is tradition, or as we should get used to doing, is verifying the model as we go. And one aspect of doing that is to make sure that the model, as you add things to it, is behaving like you expect it to. And so recall that when you place an entity instance or an object instance in Simio, it uses default parameters, default property values. And so the default property value is one server can handle the output from one source. And you have some queuing, but you don't have infinite queuing. And so when I click go here, what I expect to see is some queuing here, a little bit of queuing here, but the system is stable. And so that's in fact what we see. So that's the first step, is to place in the basic structure of the model. The second step is to specify the property values so that we can implement the arrival process and the service process. So if you remember, creating Simio models is all about using Simio expressions. And we have something that we call the top 10 expressions. So as you get more proficient at building models, we will learn how to apply these expressions. Again, this is a refresher course, so hopefully you've seen several of these. And so in our case, we need to set the property values for the source object and the two server objects. So let's do that. And so I want my source object here. I want to specify my inter-arrival time. And I'm going to specify my inter-arrival time of 10 minutes. Oops, forgot that's close parenthesis. Make sure that the time units are minutes, so random exponential 10. Then I'm going to set my service time for S1 to be exponential 8 minutes. And then finally the service time for server 2, exponential 9 minutes. 9 minutes. Time units are minutes. So we have the inter-arrival time is exponential 10 minutes. The service time for S1 is exponential 8 minutes. Service time for S2 is exponential 9 minutes. And then entities go to the sink. So just again, take a quick look back at our base model that we have the inter-arrival time 10, the service time of 8, and the service time of 9. So we're base development of the model, we're satisfied with that we have placed the object instances and set the property values according to the model definition. So before we build an experiment, which we'll do in the next video, let's build our status plot here so that we can show a couple of the interesting performance metrics. So I'm going to go to animation and select status plot. Let's just make that roughly as big as the model. To do that, I have to set the text scale here. So let's set the text scale, try that at 0.75. And then we want to have hours. Let's run for, I don't know, let's show the model for, let's run for 100 hours. So we're going to set that for 100 hours on the X. And the two things that I want to map here, or I want to show on our status plot, have to do with the number of entities in the system. So I'm going to show the instantaneous number in system and the average number in system, or the running average number in system, on the same plot. So I need to do two expressions. So if we go back to our top 10 expressions, the expressions that I need are this number in system. So default entity is the name of our entity instance, population number in system. And if I just cut that off without putting the average, we have the instantaneous number in system. And then when I use average, I get that the running average number. So let's go ahead and add those. So my expression, I'll use the expression builder this time. So default entity, population, number in system. We'll just do this one as the instantaneous. So let's just put INST standing for instantaneous. and then I'll open the repeat group editor so that I can add my second value. And so again, let's use the expression editor, default entity, population, number in system. Oop. This time I want the average, not the instantaneous, and so we will just call this one average. And so now you can see we have our instantaneous and we have our average. And so let's run our model and go back to our run ribbon, and note that we've changed significantly the pacing. So I'm going to speed this up a little bit. Let's do that 25 times. Set the speed factor to 25. Let's go a little faster than that. Set the speed factor to 50. And now you can see our instantaneous number in system is the blue line, and the running average number in system is the red line. Speed that up a little bit more. Let's go to 100 and just let that run a little bit. I guess I never did set the ending time, so I'm going to let this run. We have our plot here for 100 hours. So let me stop here and go back and set my run time. Let's just do a run length of 100 hours. So we'll leave that at 100 hours and then go back and run, and we can increase it even more. We'll increase it to 1,000 so that we can see our status plots over time. And if you remember, when we did our queuing model, we know that the exact value for the steady state number and average number in system is 13. And so you can see that we're increasing here. Here's 13, somewhere around here. And so we're not necessarily at steady state yet, but we have that expectation. And as I mentioned, in terms of verification, one of the reasons that we build the queuing model early in the process is so that we have that sense of expectation of what we are going to see when we run the model, assuming that we've done the model correctly. And so we can see our average number is increasing here, but again, it's still around this value that I expect it to be. So we can also, since we've run the model to completion, go and look at our results. And so completion of 100 hours. And so recall we have the average number in system at the completion of the run was 13.68. The average time in system was 2.26. So again, within reason relative to our expectation. We also have the utilization. So the server utilization of S1 is 90%. For S2 is also 90%, it looks like. So it looks like those values are, at least the values that we see based on our single run, are within the realm of expectation based on our queuing model. So that completes the development of our baseline model. In the next video, we're going to set up an experiment and the corresponding experimental responses so that we can go through a more formal verification process against our queuing model.